Okay, welcome everyone back to this last part of today's lecture, where we want to discuss some practical applications for electronic structures for molecules and solid states. What can we actually compute and how do we compute it in actually molecular and solid state cases? The first question in that regard we want to answer are Kohn-Sham eigenvalues actually meaningful? And during the discussion of the Kohn-Sham formalism, we discussed that the eigenvalues have no physical meaning. However, there's one exception. If we actually know the true ground state density, so in the case we have an exact DFT, then the highest occupied molecular orbital, or HOMO in short, that energy gives us the ionization potential for the given system. That's the one exception where Kohn-Sham eigenvalues actually have a meaning. However, in the 1970s or beginning of 80s, Janek basically showed that eigenvalues are related to energy changes, to meaningful energy changes, when orbitals occupation vary fractionally. What that means is that we can get meaningful eigenvalues or informations out of the eigenvalues if we vary the occupation slightly, so by adding or removing an electron. And the Janek theorem builds basically the basis for an approach that's called delta SCF, in which we can calculate the ionization potentials as well as electronic affinities in the case we don't have the exact true ground state density. How do we do that? So the ionization potential is defined as the minimum energy needed to remove an electron. So what we are doing is we compute the total energy of a system with n-1 electrons and subtract the total energy for a system, for full system with n electrons, and that gives us the ionization potential. In the exact same way, we can actually calculate the electron affinity. That's the minimum energy needed to add an electron. Here again, we compute the total energy and then we subtract the case where we add an additional electron. So we need in both cases to do two DFT calculations, one for the pristine system and then for the defective system with plus or minus one electron. And in that way we can actually compute HOMO and LUMO gaps. So HOMO is again the highest occupied molecular orbital, whereas the LUMO is the lowest unoccupied molecular orbital, and that gives us the HOMO-LUMO gap based on the ionization potential and the electronic affinity. But what about the orbitals? Are Kohn-Sham orbitals meaningful? Again, in the discussion of the Kohn-Sham formalism, we discussed that they have no direct physical meaning and are just help functions. So we should not relate them to Hartree-Fock and post-Hartree-Fock orbitals. However, Kohn-Sham orbitals often resemble Hartree-Fock orbitals qualitatively. So we can actually use them to visualize orbitals because from that perspective they are actually quite accurate. And we can do a quantitative analysis. So for example, here is shown formaldehyde and as well as acetone, and that's the HOMO -1. That's basically the orbital once below the HOMO, and that's then the HOMO. And then on the right hand side there's the LUMO. And if you check those orbitals, either for formaldehyde or for acetone, they match quite well with the Hartree-Fock orbitals. So just from plotting those, from the visualization perspective, we actually get some meaningful outcome here. Furthermore, they often match quite well with spatial and nodal structures of Hartree-Fock orbitals. So the positive and the negative layout matches usually quite well. So we can actually also use cone-charm orbitals to get out some meaningful information, which we also do in the tutorials. So plotting those can actually give us some informations. It's more like on the qualitatively point and not on the quantitatively perspective. However, it still provides informations. Okay, what happened if we move one further from molecules to solid states? How do we deal with that? So as you all know, in a single molecule we have states, we occupied our states based on the electrons in the system, and then at some point we have the highest occupied molecular orbital, the HOMO, and then the next one would be the lowest unoccupied molecular orbital, where we don't have any electrons in the system anymore. If we go to bigger and bigger and bigger systems, at the end we end up with, for example, with a quite large closed system, and here all the states are overlapping and we become more bands. So in a solid, basically all the molecular orbitals, in that case, if you want to put it in that way, overlap, and those becomes more like a continuous, and that becomes the bands. One thing we should also discuss in the term of solid states is actually the difference between a real lattice and a reciprocal lattice. Because as we see in a couple of seconds, the reciprocal lattice has actually quite influence in computing properties within solids. So understanding that concept is quite important. So the real lattice is a periodic arrangement of atoms in the real space. Our vector R is basically a sum up over our lattice parameters A1, A2, A3, and then scaled up. In the reciprocal space, we can basically set up a similar way. However, here it's made out of the reciprocal vectors B1, B2, and B3 with scaling factors. And one important thing is, the product between A1 and B1 is basically 2p. So they are, and then a delta function. So the real lattice and the reciprocal lattice are actually connected. And something quite important to note, a lattice vector which is long in the real space becomes short in the reciprocal space. Let's stick to the E image for example. We have a B value vector which is larger than the A vector in real space. However, in reciprocal space the B vector becomes shorter, whereas the A vector becomes larger. Because of the transformation we do. And one further important thing in solids are the concept of unit cells. So what is a unit cell? So all the green dots I drawed here into the real and the reciprocal lattice are basically the basis for a given system. Think about sodium chloride. We have sodium and we have chloride, and because it's a periodic pattern, you only need to know the position of one sodium and one chloride, and you can build up the whole sodium chloride lattice by just knowing those two positions, which is actually quite helpful. So the basis is basically the concept of the minimum atom positions we know within a unit cell, and the unit cell or within the lattice structure, and the lattice is our lattice vectors A, B, and in C direction. So we build up our three-dimensional unit cell basically, and then we need to know the unique atom positions, and by knowing those we can repeat the structure periodically with the formalism R or G, right? Because then we can just transform those infinitely. Okay, one thing in that regard, in the regard of reciprocal lattice and solids, is the Bloch theorem. So what does the Bloch theorem say and why it's so important? So the Bloch theorem starts from the concept that we have electrons in the periodic lattice potential, which basically equals to a 1 electron potential approximation. So our potential V depends on R, but then because it's a periodic potential, it also depends on capital R, so lower R plus R equals basically just R. So the potential is periodically, and then it basically continues periodically. So the Bloch theorem then states that in the periodic potential, electronic states are plane waves modulated by a lattice periodic function. So the plane waves we already discussed as a basis function, for example, to solve the Kohn-Sham equation. It's a similar concept. And then we have this lattice periodic function as shown here in the top right hand corner. It repeats the potential constantly, whereas the plane wave is just more like a sinus wave or cosinus wave in that sense. So the exponential expression is our plane wave, whereas the L1 is our periodic lattice function. Again, U from R or from X, it doesn't matter, is basically the same as R plus capital R. So it's get periodically expanded. So what does it mean then for our wave function? So our wave function here is basically an overlap. The real tile of our wave function is an overlap with the periodic potential, 1 electron potential, and the wave function, right? And then it basically oscillates up and down. What it means in practice is related to the Brillouin zone, because our, let's go back a quick second, because our wave function gets potentially expanded, it's enough to reduce our focus to 1 periodic unit, because of the periodicity, all the informations are already included in 1 periodic unit. And here the concept of the Brillouin zone comes in. So the Brillouin zone is the primitive Wigner-sized cell of the reciprocal lattice. So the Wigner-sized cell is the minimum polyhedra in 3D. You can basically draw in a real lattice, and the first Brillouin zone is their analogon in the reciprocal lattice. And what it basically means is that the wave factors contained in the first Brillouin zone go from minus p r to plus pr. So it has a constant boundaries from left to right, and in practice that what it means is that all our informations beyond the first Brillouin zone are just periodically repeated. So just sticking to the first Brillouin zone is enough to get all the physical informations of our unit cell. And the Brillouin zone we actually construct in the same way as we would do for the Wigner-sized cell. So if that one here is our reciprocal lattice, or B, that's more like a hexagonal lattice, we basically start from 1 point, for example that center point, and then we draw lines to the corresponding other side. So in that case to this one, and to the lower right hand corner, to the upper right hand corner, and to the lower left corner. And then that distance we halve, like this one, and then we draw the area covering that, and then we end up with that bright red area for our Brillouin zone for the first one, and then the second one would expand that, and so on and so forth. And for a hexagonal lattice we do exactly the same, but then it becomes not a square, then it becomes a 6-corner, a hexagon. Why is the Brillouin zone concept that important? Let's take a look and then assume that we have a one-dimensional periodic potential or system. If we solve the Schrödinger equation for a one-dimensional system, what we end up is that our energy values are basically a parable, right? It's h bar divided by the k, the wave vector, which sets up the boundaries, divided by 2m. And if we take a periodic continuous potential, so we need to add the g vector, right? Because that provides us information about the periodicity. And it's basically the same. It's basically h bar divided by 2m multiplied by k plus g square. So actually k is the same as ek plus g. So what it means in practice, if we have a periodic parabola potential, it basically gets continued. So that's at the 0 constant point, and then plus 1 g vector is basically at here on the right hand side. I would continue like that, and minus 1 g vector would be on the left hand side. Sorry, my drawing skills are not great. So that potential gets periodically evolved, and in that case it's quite often the case that we so on the left hand side, that's sometimes called as an extended zone schema, where we just have the whole parabola solution solved. And then on the right hand side it's called periodic zone schema, because now we take also g into account. And then the center part, which is usually just used as the reduced zone schema. So we can just focus all our attention to the first Brillouin zone, because everything else gets basically reprojected into the first Brillouin zone. Even if we take the periodic zone schema, right? If we start, that's our first Brillouin zone here and here, and you can see that arm here as well as the arm from the left hand side are the periodic boundary potential informations re-emerging in the first Brillouin zone. But we can also do that from the extended potential. We start here, that's our first Brillouin zone again, and what we could do is we could reflect or reshift that part of the potential by plus 1 g vector, right? But plus 1 g vector, we would shift that like here, and then we end up with that, and the right hand arm minus 1 g vector would us lead up here, and then we end up reflecting the potential. So it's completely enough to focus our attention on the first Brillouin zone, because by applying translational informations onto our potential, we can completely compress all the informations in the first Brillouin zone in the reduced zone schema. So we get all the band structures, for example, here move back into the first Brillouin zone, where we then can get our band structure, band gaps, and so on out of. So the first Brillouin zone has a quite important meaning for solids. What it then means in practical applications, right? You're all more or less aware with the concept of an isolator, where our valence band is fully filled and then the conduction band is basically empty, and in between we have the Fermi edge, and the Fermi edge basically provides us with information until where the bands get filled. then a metal has basically a filled valence band, and the Fermi edge lies in between, lies in the conduction band. So the conduction band is partially filled. For that reason, we have a conductivity, and we get a metal. And for the isolator, sorry, our Fermi edge lies in between basically valence band and conduction band. And if we quickly jump back to the Brillouin zone, right, that's exactly the thing. That's the first parabola, basically our first band, and then the second one here, those arms are our second band, and that's the case for free electrons. If we have nearly free electrons, then the solution would slightly differ, and we get actually separated bands, how you would expect from a real solid. And then last but not least, in that scheme, we have the semiconductors, where basically, right, our Fermi edge lies somehow in between, also valence band, conduction band, but it can be overcome, for example, with thermal energy, and then electrons from the valence band can move up towards the conduction band and contribute for conduction. So the Fermi edge is quite important also concept in that sense here, and I would like to point out that first of all, right, the Fermi edge marks the energy of the highest occupied states, and then for practical applications, when we use the Fermi edge to model our solid properties in DFT, there's usually a smearing parameter, and in the last part of that lecture from today, we discussed it quickly at the end for the practical applications. What happened if your SEF cycle does not converge? So what we assume at 0 Kelvin, right, is, or what the Fermi edge is at 0 Kelvin, it's a step function here in red, right? So the highest occupied states are basically just filled up until one given threshold, and then they are empty above. So with that, it's basically filled, and then not filled at all. However, in the moment where we apply temperature, and DFT is a 0 Kelvin method, so we have to think about how to deal with the real nature of a material system. Is more like that we apply a slightly smearing of the Fermi edge, and that's usually a parameter we also add to our DFT calculation, and you might need to check those because your smearing parameter is either too tight or too loose. And what it means in practice is that the electrons, because they get some thermal energy, right, and the ones close to the Fermi edge, because they get the thermal energy, they jump out of the valence band and go towards the conduction band. So your step function becomes a bit more soft, and that's basically what that smearing here shows, right? At whatever 1200 Kelvin, that's quite warm. But even at 300 Kelvin, at room temperature, right? The green one here, that one, you see actually that parts of the electrons, right, from the occupational side of the diagram move towards the unoccupational, basically to the conduction band. So you get a slight smearing effect by applying temperature, and that's also what we do in our DFT simulations. Okay. And one thing, if we actually compute the band gaps, right, so we applied the smearing in our DFT calculations to a bit more realistically, for example, to compute our band gaps, right, and then what it basically shows is that LDA provides the worst band gaps. I mean, the famous example is silicon, which has no band gap at all in LDA, and in practice it has a band gap of around 3 electron volts. So it's quite noticeable that LDA is not suitable to compute band gaps, especially then for silicon. GGA is better, but still not great. And then hybrid is usually what people deal with to compute band gaps. That still usually underestimates the reality, but it's a good approach to a good way to compute band gaps. So keep that in mind. If you want to compute a band gap, choose the right method, right? What usually the approach is here, that you do a structure optimization with either LDA or GGA functional. Let's say with a PBE, which is a GGA functional, you do the structural relaxation, and then on top of that structural relaxation you set up a hybrid functional calculation like an HSE06 and solve the SEF cycle only once. So you don't do a structural relaxation with a hybrid because that would be too expensive. You just do a single point calculation, and that provides you with more suitable band gaps. Okay, last but not least, the practical implementation of the first Brillouin. So we now spoke a lot of, we can reflect we can take advantage of the periodicity of our potential. So it's enough to focus our attention on the first Brillouin. But what does it mean in practice? So in practice, right, all possible eigenstates are defined as a wave vector in the first Brillouin. So just integrating over the first Brillouin gives us all the physical information we actually need. However, in practice we don't do that. We don't integrate over the first Brillouin. We use usually something, for example, a concept called Moncost-Pack grid. So we divide our first Brillouin into a grid pattern. So the green points are basically the grid pattern. So in that case, our Brillouin would be separated into two grid points, 1 and 2, or technically here, but that's the one from the third one. And what we do is we don't integrate over the first Brillouin. We just calculate the density at given k-point grids or a mesh, and then our density becomes not an integral over all the density states, but it becomes just a sum over the density states for given k, for given wave vector k. And for that reason, choosing your k-point grid is quite important. If you have a too loose k-point grid, then your density is not suitable enough, because you just integrate, or you just sum up over a few really spare distributed points within your first Brillouin. Making a k-point grid too narrow, you pay the price. I mean, sure, your density becomes quite accurate, but for the price of summing up over more and more over more k-points. So here, finding a good solution is quite a challenge. So you want to always test the number of k-points, right? If those are suitable to provide you the needed accuracy, but are they too fine, too accurate, right? If you add more, at some point your accuracy doesn't grow in the same way, right? So just choose a decent amount of k-point grids within your Moncost-Pack grid to not overpay the price for your calculations. And that's how we deal in practice then, calculating with the density and solving electronic structures for solids. So let's sum up the lecture from today. So we discussed 5 topics. First of all, the exchange and correlation functionals and the concept of the Jacob ladder. We then discussed a bit more in depth the concept of local density approximation and the generalized gradient approximation. We spoke about dispersion interaction and the need to correct them in DFT because we underestimate non-covalent interactions. We spoke about practical informations and implementations of DFT, about the self-consistent field method. And last but not least, we discussed electronic structure and how to implement and how to compute those, and then what to get as how to compute practical material parameters for molecules and solids. So in conclusion, right, we saw that the exchange correlation functional needs to be approximated, and we have 5 different ranks balancing between accuracy and cost, and it's basically LDS rank 0, whereas double hybrids are rank 5. We also discussed that most of those functional underestimate non-local, medium and long-range interactions like the van der Waals interaction, so we need to correct them in order to get the right dispersion interactions. And we discussed that the SCF cycle is an iterative method to solve the Cohen-Sham equations. And last but not least, in solid state physics, basically the first Brillouin zone contains all the physical relevant informations, so we can use the reduced zone schema to reduce our analysis to just the first Brillouin zone to get all the relevant informations for a solid with DFT, or I mean in principle, but also with DFT. Okay, with that we are at the end of today's lecture, and then in next week's lecture we will discuss machine learning interatomic potentials.